Hello, and thanks for tuning in to my video poster. My name is Andrew Beveridge, and I am a professor at Macalester College in St. Paul, Minnesota. I'll be talking about 3.2-1 avoiding permutations with maximum inversion number. This is joint work with my Macalester colleague, Kristen Hesse, and our former student, Paige Robertson, who is currently a graduate student at the University of Colorado Boulder. And I just wanted to take a moment to thank the organizers for putting together this conference and for including me in this virtual poster session. So let's get started. The inversion number of a permutation is the number of pairs of elements that appear out of order in its one-line notation. For example, this permutation has inversion number 5 because 1 and 2 appear after 3, 4 appears after 5, and finally 4 and 6 appear after 7. The identity permutation has inversion number 0, while the reverse permutation has the maximum inversion number since every pair is out of order. So let's talk about classic 3-2-1 avoiding permutations for a minute. A permutation pi is 3-2-1 avoiding when there do not exist I less than j less than k such that pi of I is greater than pi of j is greater than pi k. So we can't find a triple that is out of order. We'll denote the set of 3-2-1 avoiding permutations by Sn of 3-2-1, and it is well known that this family is enumerated by the Catalan numbers. So here is our warm-up question. Among 3-2-1 avoiding permutations, what is the maximum inversion number, and how many permutations achieve this maximum? This question is straightforward to resolve. It is well known that pi is 3-2-1 avoiding if and only if we can partition the permutation into two strictly increasing subsequences. And here is an example of such a permutation for n equals 8. It can be partitioned into the subsequence 3, 5, 7, 8 and 1, 2, 4, 6. After we've partitioned pi into subsequences of length m and n minus m, then the most inversions that we can possibly have is their product, m times n minus m. In fact, we can achieve this value by putting m plus 1 through n at the start of our permutation and placing 1 through m at the end. Now, to maximize our inversion number, we want to take m to be as close to n over 2 as we can. So when n is even, there is a unique 3-2-1 avoiding permutation that maximizes the inversion number. And when n is odd, there are two of them. This brings us to vincular patterns. Rather than looking at 3-2-1 avoidance, let's look at 3-2-1 avoidance. In this case, the first two entries in the forbidden sequence must be adjacent to one another. Clayson proved that the family of 3-2-1 avoiding permutations are enumerated by the Bell numbers. And the goal of this video is to resolve the following question. What is the maximum inversion number for 3-2-1 avoiding permutations? And how many permutations achieve this maximum? So let's introduce a couple of symbols. Maxinv Sn 3-2-1 is the maximum inversion number that we are interested in, and Zn of 3-2-1 is the set of permutations that achieve this maximum value. Here's an informal statement of our main theorem. We'll delay the full statement for a few slides to avoid introducing lots of symbols all at once. Basically, my collaborators and I have proven that both of these sequences have matches in the OAIS. We've given new interpretations of these sequences, and we give new simple formulas for them as well. And we'll see that each of these sequences is the sum of two binomial coefficients. So let's talk about how to get a handle on this problem. We need a representation of our permutation that showcases its inversion number, and for this we turn to the lemma code for a permutation. Given an n permutation, we create a list of length n whose ith entry counts the number of larger indices that contain permutation values smaller than pi I. Let's look at a small example of how to construct a lemma code for a given permutation. We start with a candidate list containing the elements 1 through n. We then process our given permutation from left to right. At each step I, we record the number of elements that we must skip over to get to pi I. For example, let's look at the permutation 3, 1, 4, 2. Our first value is 3, and we must skip over 2 elements to get to 3. So we record a 2 and remove element 3 from our candidate list. The second entry of the permutation is 1. We don't need to skip over any elements this time, so we record a 0 and remove element 1 from the candidate list. The third entry is 4. We have to skip over the 2 to get to the 4, so we record a 1. Finally, we record a 0 since 2 is the only element remaining in the list. It is simple to see that the ith entry of the lemma code is at most n minus I, and that the sum of the lemma code entries gives you the inversion number of the original permutation. Now let's characterize the lemma codes for 32-1 avoiding permutations. We have shown that every decrease in the lemma code must go all the way to 0, and this is an if and only if condition. We find the visualization on this slide very helpful. We start with the staircase shape and fill in the columns corresponding to the value of the lemma code. As this example shows, the lemma code consists of weakly increasing subsequences separated by one or more zeros. For convenience, we're going to make two small alterations to this lemma code. First, we're going to drop the final entry, which is always 0, and then we are going to reverse the sequence. Trust me, this makes the indexing of our arguments much more intuitive and manageable. So now we have a family of sequences that are equivalent to the lemma codes for 32-1 avoiding permutations. These sequences have to fit in this reversed triangle template, and now they consist of weakly decreasing subsequences separated by zeros. We decide to call them jump float sequences, since you repeatedly jump up from 0 and then drift back down as slowly as you like. The only rule is that you can only increase or jump when you are currently at 0. And finally, we define the weight of a sequence in the natural way. We sum its entries. So the weight of a jump float sequence equals the inversion number of its corresponding 32-1 avoiding permutation. Now these jump float sequences have a natural poset structure. One sequence precedes another when its entries are element-wise smaller. In this case, we are looking at the jump float sequences of length 3, which correspond to 32-1 avoiding permutations of length 4. We have 3 maximal elements, but only 2 of them, in orange, achieve the maximum inversion number, which is 4. On this slide, we give an algebraic characterization of maximal jump float sequences, but it is much more intuitive to use the triangular representation. What we are doing is packing rectangular boxes underneath a staircase. The one rule is that different rectangles must be separated by a column. The 32-1 avoiding permutation with maximum inversion number corresponds to a rectangle packing with the largest area. As we saw for the post set when n equals 3, being maximal does not guarantee that you have maximum area. Perhaps this is more clear when we consider a larger example. Here are the 8 maximal jump float sequences for n equals 5. Among them, 3 achieve the maximum weight of 10. It is routine to show that the number of maximal jump float sequences is the Fibonacci number, but it is very challenging to show that the maximum weight sequences are counted by this sequence from the OAIS. The key to solving this problem is to reorganize the sequence into the trapezoid that you now see. The pattern that I'm hoping reveals itself to you is that we have a Pascal-style recurrence. The value of an interior entry is equal to the sum of its northwest and northeast neighbors. And this Pascal-style recurrence is precisely what we need to prove about the triangles for our jump float sequences. Now that we've organized our data into this trapezoid, we can state our main theorem for real. Given a size n, locate its location in this trapezoid. For example, if n equals 10, then we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And see that n equals 10 corresponds to this first 7 in the third row. So we take rho sub n to be the corresponding row, in this case 3, and we take lambda n to be the corresponding column using a 0 index. So in this case of n equals 10, our index of the column is 0, 1, 2. Then the number of maximum weight jump float sequences is the sum of these two binomial coefficients, which depend upon rho and lambda. The maximum weight is given by this sum of binomial coefficients, which depends upon n and rho. Let's rephrase this result in terms of our original problem. The first equation gives us the number of 32-1 avoiding permutations that maximize the inversion number. The second equation gives us that inversion number. In the time I have left, I wanted to show you some of the highlights of the proof. The first thing that we do is represent our maximal jump float sequences by listing the widths of the rectangles. This is enough information to recreate the sequence itself. Next, we show that if our sequence has k rectangles, then the size n must be in row k-1 or k of the trapezoid that I showed you. That really cuts down on the possibilities. After that, we show that if our sequence has k rectangles, then the widths of those rectangles are also very restricted. the ith rectangle must have width I-1 or I plus 1. Now we have enough information to resolve the leftmost diagonal of the trapezoid, where there is a unique maximizer. In this case, the widths of the rectangles are very satisfying. In the kth row, the widths are the numbers 1 through k. This brings us to the Pascal-style recurrence of the proof. We're able to argue that if we are in row k, then the last rectangle has width k or k plus 1. We then use induction to fill in the remainder of the rectangle packing using the northwest and northeast neighbors of our problem size. So that's the high-level view of our result. Once again, we were able to fully characterize the 3-2-1 avoiding permutations with maximum inversion number. Thank you so much for watching this video.